Hello, good morning and welcome back to the Nexperia Power Live Automotive channel. We're here with you live for another 90 minutes and we continue our discussions now with technologies for automotive 48 volt hybrid. The session is scheduled for approximately 25 minutes. We will start with a presentation and then, like before, open the floor for questions. So you can contribute any questions, remarks, or your own experiences or thoughts by using the speech bubble in the bottom right of your screen, and all contributions are anonymous. With us today, we have Reza Betash from Application Marketing, Ian Kennedy, Strategic Marketing Manager, and they're also joined by Mark Fang, Principal Application Engineer. So with that, I'll hand over to Reza to begin.
Thank you very much, Kelly. Okay, let's start with this slide, which is showing the Nexperia solutions for 48 volt hybrid system. So the 48 volt systems came up due to some government regulations in order to reduce the carbon footprint of cars. And you see here the range of products which Nexperia offers for these kind of applications. So starting from power diodes and transistors to ESD protection, of course, MOSFETs are a very important part, and also logic devices. And on this picture, two applications are highlighted, the DCDC converter and the belt-driven starter generator. These two applications are crucial and are transferred into the 48 volt bus system. And today we will focus on the DC-DC converter and on a sub-application within DC-DC, which is the auxiliary power supply. Okay, so let's continue with the DC-DC converter. So the design considerations, as you can see here, are that the converter needs to work in buck, but also in boost mode. That means the converter needs to be bidirectional. So the power is converted or transferred into both directions from 12 volts to 48 volts, but also vice versa. And yes, so some technical value propositions regarding the products. So regarding MOSFETs, obviously you need a low RDS-on MOSFET, but beyond that, you need a soft and efficient switching, which Nexperia MOSFETs have. They come in a very reliable package. They have high robustness against avalanche, and specific types can be also used in linear mode. Then we have a very huge portfolio of ESD protection devices covering almost all the possible interfaces in the car. For example, like CAN or CAN-FD. And last but not least, we have a huge portfolio of discrete rectifiers. We have Schottky rectifiers, but also trench Schottky for a higher thermal robustness and also for a lower leakage. And very recently also a novel technology called silicon germanium. The power levels we are talking about are roughly 3 kilowatts, which is transferred by the converter. Okay, this is the high-level functional block diagram of the DC-DC bidirectional converter. The most important part is, of course, the power stage. We come to that in a minute, consisting of two switches. By the way, the areas highlighted in pink are the areas where Nexperia can offer a solution. Okay. And before going to the power stage, I would like to continue with the auxiliary power supply as a sub-application. And the auxiliary power supply is needed in order to power the microcontrollers and the logic and the control electronics of the car or of the system. So as you can see here, it is a flyback converter, and on the primary side, obviously we need a switch, NMOS switch, And here we suggest to use a MOSFET switch in the range of 40 to 60 volts in an LFPAC 33 package. And this is this family of products you can use. Of course, they have a low RDS on, but also you need a high switching frequency in order to keep the size of the passives small. The transformer will have kind of leakage inductance, and in order to protect the MOSFET, you need a clamping circuitry. And here we suggest to use the Schottky diode in combination with a TVS diode in order to dissipate the power in the leakage inductance. And of course, this clamping circuitry needs to be highly reliable, which is the case for our products since they are AEC-Q qualified. On the secondary side, we have the typical logic levels which you need. That means 3.3 volts and 5 volts. And so one needs a Schottky device for the flyback converter on the secondary side. And here we suggest our PMAC family, and but also our silicon germanium if you have a very demanding design with a high ambient temperature. Okay, and with that, I would like to hand over to Ian.
Thanks, Reza. Good morning, everybody. So, yeah, I mean, the DC-DC converter forms really the heart of that 48-volt mild hybrid system. It's, as he mentioned, it's there to increase the efficiency of the system, but also to provide a stable power supply. Even when the car is going into these different modes of sailing or start and stop, you still want all of those 12-volt electronics to be working. So your DC-DC converter is spending a lot of its time delivering power to the right-hand side to the 12-volt loads to keep things going there. Now, what we see on the screen is the DC-DC, the heart of the DC-DC in the middle, the main converter with 80-volt MOSFETs. So you'd have a high-side MOSFET and a low-side MOSFET. But then to the left and the right, on the left, we have the 48-volt side. And there you would need some form of short-circuit protection. Again, that would be an 80-volt MOSFET. You've got a 48-volt battery on one side, so you need a higher voltage grade MOSFET. And on the right-hand side there, on the 12-volt side of the converter, there you often have back-to-back MOSFETs. So you've got both short-circuit or safety switch, so you can isolate the DC-DC, protect wiring and those kind of things. But you've also got a reverse polarity MOSFET there, just in case the cables are flipped the wrong way around. So as I say, it spends a lot of its time in the buck mode. It is a bidirectional converter. That's what we often see. Power can flow in two directions, depending on the mode of operation of the vehicle. And then that places different stresses and strains on the components within that system. So if we move to the next slide. So this is now a picture showing drilling down into the main converter there. Although it's 3 kilowatts, often what you see is multi-phases. Within Nexperia, we've actually created our own demonstrator of this, which is at 750 watts, and then you can just replicate that several times. The high side MOSFET is shown here, Q1, and the low side Q2. The main, it's quite a fast thing, the DC-DC. They're often running at kilohertz. So the MOSFET components need to have very good thermals, need to be in a good solid package. The LFPAC is perfect for that. But the technology, the silicon technology, needs to be fast, but also smooth. So you don't want to be generating lots of noise in the DC-DC that then radiates, but it also needs to run cool. So you need a low resistance MOSFET as well. So on the right-hand side, we try and capture the kind of system requirements and mapping that across to the MOSFET requirements. So low on-state losses means you're not generating heat, so you need low on-state RDS on. That's something we're very well aware of and have been doing for 20 years, so that's a natural thing. What's new really, though, is the soft and efficient switching, which in automotive hasn't been there for a great deal of time, but is something now that Nexperia is focusing very heavily on when we're building the technologies that we're bringing to the market now. And then the fundamentals of automotive, it's got to be reliable. You know, this is a very important part of the powertrain system. So we need to ensure that the products we're delivering are fundamentally going to do the job they need to do. Okay, so if we move to the next slide, well, what kind of technology are we bringing for that? Well, our solution for 48 volt is what we call our Trench 12 technology. It's the 12th generation of MOSFET technology from Nexperia. So you can imagine we've been doing this for a long time and have a lot of solid engineering experience in bringing new MOSFET technologies to the market. It's a unique technology that we have. Although we would describe it as a deep trench split gate, but it's quite novel in the structure in that you're having the gate just to the left and the right of that source field plate. It acts based around reserve technology. So it's yeah, I would say that there's no compromises there in terms of reliability. So around the technology, we're still putting it in things like the LFP packaging. And for ourselves, we always test to at least twice Q101. Q101 is the automotive standard for qualifying MOSFET technologies. We double that every time we bring a new technology because we want to understand where the edges are and demonstrate that our products are not going to cause any issues in the field. So it's got a very high mechanical robustness, and the silicon technology is tested out to ensure that it's meeting all the requirements and needs that are there. In terms of power density, of course, you've got 3 kilowatts. You've got to try and get rid of this heat. So the RDS on, the R spec for this technology is very low, which means you can deliver less than 1.7 milliohm maximum RDS on. So typically, you'd be at about 80% of that. So it's very, very low resistance for a single switch, and you're putting often those in parallel as well. So you're always driving down that resistance. The packaging we have is a copper clip technology. The LFP 88 is perfect for this kind of application. Inside that package, the silicon is connected to the outside world via what is effectively a bus bar, big slab of copper, which means you can get very, very high currents through it. And it's a very efficient package. You know, we're the efficiency company. So when we're building these packages, we're making sure we can squeeze as much silicon into as small a space as we can. So it's smaller than a D2 pack or some of the other packages we see out there, which means that your real estate is lower. You can make a smaller, more compact solution, which is then more efficient in the job it's trying to do. And I mentioned before the soft switching, and we'll come on to a bit more of that in a moment. Now, the Trench 12 technology itself will be rated at 80 volt or 100 volt, and will bring both a standard level gate and a logic level gate flavors of MOSFETs to that. So you can imagine a portfolio of somewhere between 50 and 80 MOSFETs to address these kind of 48 volt systems. Okay, next slide. So one of the key parameters that we're looking at and want to talk about today is this need for soft and efficient switching. We've already said we're trying not to build a radio in the car, we want to build a DC-DC. So one of the tests that we do regularly on new technologies as we're developing them is called double pulse test. We've got the circuit for that shown on the left-hand side. So we have a high side MOSFET where the gate and the source are shorted. So it's really just acting as a diode and recirculating. And on the bottom, in the low side, that's the active MOSFET that we're switching on and off and on and off, hence the term double pulse. And then we're looking at the waveforms in that circuit as we get the diode behavior comes out, and also we're looking for voltage overshoots. So we want to ensure that the device is not ringing like a bell, and that the energy, the losses are very low. And that's really what's trying to be shown in the middle and on the right. So the body diode behavior is what's really giving that softness metric. And the switching losses, how much energy it takes to turn on and turn off, is what's bringing the efficiency. If you couple that together with normal on-state losses, low RDS on, you get something which is very, very efficient. Okay. So this is the, it's a very early test that we've made on some early samples that we have. So it's an 80 volt MOSFET. in our LFPAC 56E package or SOT 1023. 3.3 milliohms maximum, 80 volt, standard level gate. We put a 10 ohm resistor on the front of that because we really, in our double pulse, we always want to test the edges. So we drive them very hard and very fast, much faster, maybe an order of magnitude faster than we would do on datasheet, because we want to see what the behavior is and make some comparisons to our previous technologies. The waveforms are shown in the middle, so let's just go through those. So the purple trace is the low side VDS, so that's the voltage drain source. So you can see you're going from a high state to a low state. The gate source voltage is in a blue color, VGS. So you can see you're going from off. In this case, you're going from an off to an on state. And then the high side VDS, just working down, is in a sort of gray color. And the high side is going from low to high. So you can see it's a turn off. So the bottom's going on, the top one's going on. And the current is in a kind of greeny cyan color. And as you follow that through, that's the energy that you see, the hashed area is where we're looking at the efficiency. So we want to try and minimize that area as much as we can when the body diode is recovering, when you're commutating between the on and the off state. So you can see there a relatively small area. We're looking at 16 microjoules of energy during that turn on. So during turn off, it's something like about 8. So it's about 24 microjoules of energy for every switching event. And if you remember, we spoke at the front end about these systems running at tens, if not hundreds of kilohertz. So that becomes a very important factor. If every time you're dissipating microjoules, if you do that millions of times, then suddenly you're going to end up having quite a lot of energy to cope with and start to do good heat sinking, which I'm pretty sure, yeah, the guys that are on the call, that's something you're very aware of and something you build into your designs. But we try and minimize the amount of heat we're generating in the first place. So rather than having to manage it when it's there, just don't generate it. It's the easy way to do it. So we've got the IRM is shown there, the efficient switching. And now on the softness, that really can be picked up by looking at the high side VDS. So what you're trying to achieve is what we see on the picture. So it's an 80 volt MOSFET. So avalanche breakdown voltage is about 80 volts. And we can see that the overshoot is going to about 58 volts. So it's well below that avalanche event. This MOSFET is a really nicely controlled MOSFET in terms of its softness. So you've got a very low first spike or low burst overshoot. And then you can see the ringing, the softness over 3 or 4 oscillations, and it's down to something very soft. So you're not getting a very high voltage overshoot and then ringing like a bell. Here we've got something which is damped really nicely. So it's a measure of the technology. It says fundamentally the design of the technology is there and delivering what looks to be a very nice, soft and efficient result. Okay, so I think with that, thank you very much for listening today, and please, we welcome your questions.
Thank you, Ian. Thanks, Razor. Okay, let's open the floor for questions. Just to remind you, if you do have a question to ask, you can do so using the chat button in the bottom right-hand corner of your screen. We don't have much time, so let's move straight in. Are there any more applications for the 48-volt bus? Ian, would you like to maybe?
Okay, yeah, sure. So and that's a good question. So what we see, the very first, the emergence of 48 volt when it came in, the first thing that people were trying to do was get the efficiency of the overall system down. So reduce your CO2, improve your fuel efficiency by looking at the powertrain. So you introduce a 10 kilowatt belt starter generator to start and stop your engine, do some boosting and things, and that immediately gives you 10 to 15% CO2 efficiency. Now that you've introduced a new voltage bus into the car, then we expect to see more and more systems going on to that, and they'll tend to be the large ones. So compressors, or we've seen reports that are in the public domain that talk about putting things like power steering on there as well. So the larger loads that are on more, we would expect to go onto the 48-volt bus first, because it's there, it's available. You should use it. So it's compressors, air conditioning. So, you know, large, several kilowatt kind of pumps and motors would be the first ones that we would expect to see coming on.
Okay, thank you, Ian. On to the next question. What role is gallium nitride presently playing in 48-volt hybrid power electronics?
Low voltage GaN, very little. So the advantages of GaN we understand to be more around that super fast switching end. So you'll see it occasionally in, I think LiDAR is probably a great example of where we would expect it to add value over time. But not so much in the power electronics. In the high power electronics, the motor drives, the DC-DC at the moment, we're still seeing that silicon is, there's still a long way to go with silicon yet. So that's still providing and delivering what it needs to do in that space.
Okay, thanks, Ian. Do all 48-volt, 12-volt DC-DC converters need the safety switches?
So Mark, that's probably one for you.
Yeah, I can take the questions. So I think for the structure that the 48-volt battery is the main battery for the car. So it should have the battery measurement system and some safety inside. But the 48-volt still needed the short circuit protection MOSFET. And from 12 parts, the 12-volt battery is usually a lead acid battery. So it should need a back-to-back protection for the 12 side. And also it will be useful for some time you want to active control for the circuit. So the safety switch we just show in the diagram, just like this.
Okay, thank you very much, Mark. We've probably got time for one extra quick question. When do these MOSFETs become available?
Okay, so the Trench 12 MOSFET, at the moment we're doing early sampling now. So we have samples of 80 volt and 100 volt technology in the LF pack 88 and 56E available today for early testing. We'll move to something like an engineering sample towards the end of this year. And then in the second half of next year, qualification samples will become available for customers to do things like their C builds. So if you're looking at an SOP for 2022, 2023, then Trench 12 is a perfect fit in terms of timing. You should be considering that.
Okay, thank you very much, Ian. We do have a couple more questions, but unfortunately we're running a little bit short on time this morning. So what we'll do, as with some of our other topics, we will collate all the questions asked. We'll get our power experts to provide some answers, and we will upload and publish a Q&A document after the event. So in the meantime, that brings us to the end of this particular discussion. Thank you very much to Ian, Reza and Mark. If you want to know more about this topic, there are resource links underneath this screen, but also you can chat live to one of our power experts throughout the day. So just use the chat function on the website. If not, just stay around. We've got a break of about 5 minutes, and then we follow with our next live discussion, which is our new P-channel LF pack automotive MOSFETs. Thank you.